Today I am going to explain about lanthanides. They are so similar to element of lanthanum. Lanthanides, also called rare earth elements, comprise of a group of 15 elements of which only one, promethium, does not occur naturally in earth crust, while the other 14 are relatively abundant in rock and solids. The series of 15 metallic elements from lanthanum to lutetium are called lanthanides. In these elements, the differentiating electrons enters 4f orbitals. Position in periodic table. In sixth period after lanthanum, the incoming electrons enters the 4f orbital, and the following 14 elements are called lanthanides or lanthanones. Placed outside the body of main periodic table, as they resemble each other very closely, and keeping them inside the main table will overrule periodic law. Electronic configuration. The general electronic configuration of these elements in ns2, n-1, d0 to 1, n-2, f1 to 14. They resemble each other very closely as they have same electronic configuration in n and n-1 valency shell. An alternate electronic configuration is also suggests that after cerium, the d electron also shift of 4f orbital, except for those elements where it will disturb f1 or f14 configuration. Lanthanide contraction. They study decrease in size of atoms and ions of the rare elements with increasing atomic number from lanthanum through lutetium is known as lanthanide contraction. For each consequent atom of nuclear charge increased by 1 unit accompanied by corresponding increase in the number of electrons present in the 4f orbital. The new electrons enter the 4f orbital, which have very poor shielding effect due to their diffused shape. As the result, nuclear attraction increase and electron shell attraction. Consequences among lanthanides. Basicity of ions decrease from lanthanum to lutetium, so their oxides and hydroxides are less basic. As the atomic size decrease across the series, the elements following lanthanides show change in the physical properties. The ionization potential increases, metallic nature decreases, electropositivity decreases, electronegativity increases, tendency to form complexes increases. Post-lanthanides. Occurrence of elements as their pairs. Due to similar size of 4d and 5d in group, they have similar physical and chemical properties. They occur together in nature and their separation becomes very difficult. Densities. 5d elements have very high density as down the group there is large increase in mass but occurrence no increase in along volume. With heavier lanthanides, yttrium has similar charge and size to holmium 3+ and europium 3+, hence it occurs with and separation is difficult. Oxidation state. The configuration of lanthanum 3+ ion is that of xenon, which is highly stable. So it is not possible to have lanthanum 4+ ion. In the same way, GaLu also form only 3+ ion because the removal of 3 electrons gives stable half-filled 4f7 configuration for Gd 3+ ion, and in completely filled 4f1 to 4 configuration of Lu 3+ ions. In other lanthanides, +2 and +4 oxidation states also occur, but these are always less stable than the +3 oxidation state, which is characteristics of this family. The 2+ and 4+ oxidation states are shown by those elements which will attain F0, F7 and F14 configuration by doing so. For example, cerium 3+, europium 2+ and 4f7, Tb4+ minus 4f7, Yb2+, 4f14. Extra stability is associated with F0, F7, F14 configurations. Magnetic behavior. Lanthanum 3+ and lutetium 3+ do not contain any unpaired electrons, so they do not show paramagnetism. All other tripositive ions of lanthanides are paramagnetic. The 4f electrons are deep inside the ion and are well shielded from the quenching effect of the environment. The 4f orbital are well shielded from the surroundings by the overlying 5s and 5p orbitals. As a result, the electric field of the ligand surrounding the ion does not restrict the orbital motion of the electron. Mu s plus s equal to root of 4s s plus 1 plus l plus 1 s spin contribution, l orbital contribution. The magnetic moments of tripositive lanthanide ions are plotted against their respective atomic number. The value increases up to neodymium 3 plus and then drop of samarium 3 plus. Separation of lanthanide. Solvent extract method. This method is based on the difference in partition coefficient of lanthanide salts between water and organic solvents. The solvents employed in this method of extraction of the lanthanides are usually tri-N-butyl phosphate and diphosphoric acid. For example, GDNO3 can be separated from the NO3 by continuous extraction with water from the salt exchange method, and synthetic ion exchange resin with functional group like COOH and SO3H is packed in a long column fixed in a vertical position. The study decrease in size and consequent decrease in basicity causes the study decrease the complexing ability with increasing atomic number of lanthanides. When an aqueous solution containing the mixture of trivalent lanthanide ion M plus 3 is passed through a column having synthetic cation exchange resin solid, the M plus 3 ion replace H plus ion of the resin and thus get fixed on that.